All right, so welcome to the second part of chapter 1. And the previous lecture, we looked into introduction about what's payment management system is all about. But really, what's very important also is to help us in any payment management system is to know how do payment fails and how can you distinguish what kind of distress or what kind of problem do you see in the field, as well as what can be the cause and how can you fix it. Those are the main factors and the main questions that you have to ask yourself as a pavement engineer going to the field. You're trying to identify what's going on there, is to know the reason, what's the problem is, what might be the cause, and how can it be fixed. Today we're going to discuss how do pavement fails. Pavements, again, there are two major types of pavements. One is flexible pavements and one is rigid pavements. Flexible pavement is basically the most well-known one, which is a mix between asphalt as a liquid asphalt as well as aggregate. We mix them together, and that's what we call flexible pavement. Whereas rigid pavement is basically concrete. So it's water and concrete, water and aggregates. Sometimes it's reinforced, sometimes it's not. So let's start with the how do pavement fails and what are the common types of failures that we see in hot mix asphalt. So HMA for the new ones, which we do have multiple new students. So it's hot mix asphalt. And PCC, that's Portland cement concrete. All right, so what are the basic HMA pavement distresses that we see? One of the main problems that one of the major enemies of any flexible pavement structure is actually drainage and water. Water is enemy number one for any pavement structure. If you do have a poor drainage condition, you're gonna end up with pictures like that. If water get in contact with aggregates which are rocks, they would have higher tendency to interact chemically with water rather than asphalt. So what happens is, again, you get to see these pictures here. Just those are just examples of these pictures, and basically it's very hard to fix those issues. Most of the time we have to have a major reconstruction here. The best way to fix it is to prevent it by having a good drainage system. Otherwise, again, we end up with major reconstruction. The picture here is also related to it, which is water bleeding and pumping. What does that mean? Water bleeding and pumping. What happens is, with time, when water goes all the way down to the below the surface of the pavement, it's gonna start now to pump the fine materials underneath the hot mix asphalt. So let me draw for you a typical cross section. So the top layer is hot mix asphalt, and then I have a base, and then I have a sub base, and all this on top of the soil, or the technical or fancy word for it, subgrade. So once water penetrate all the way to the base and sub base, the base and sub base, those are crushed aggregates that they are just, again, good aggregates crushed really well, and that's about it. And aggregates, when it's crushed, you're gonna end up with all kinds of sizes. You're gonna have, again, up to three-fourths of an inch or even an inch worth of a big gravel piece, but it can be all the way down to very fine materials. When water gets into the base or sub base, and now let's say I have a vehicle here moving, and there is a crack here, and the water is all the way to the base or sub base. What happens is the water will take, now the vehicle is approaching that crack, so it's gonna add a lot of pressure, and this piece of the asphalt is gonna actually bend a little. and it's going to create pressure. That pressure is going to let the water take some of the fine materials that they are low in weight and pump them to the surface. So these fine materials with time will be pumped with the water all the way to the surface. And that's why we call it water bleeding, and sometimes we call it pumping. We pump the fine materials at the top. What would that do? What would that do is basically it will weaken the layers underneath hot mix asphalt. So sometimes, and we see this sometimes when a flash flood were to happen, and um, a major damage will happen. Actually, the whole hot mix asphalt section will just sink. Because really the hot mix would be still intact. But what happens if we're losing the support that's coming from the base and the sub base, then the whole system again is gonna fail. So again, a major problem here is to prevent the water from getting into the base and the sub base. What happens after that, or due to pumping, and if pumping continue to happen, we see also again depression. This is maybe again the beginning of it before we have a major failure, where now at this point here, if you go to any location and you start to see that really the surface looks something like this, the cross section. So really the movements, there is like depression towards the crack, going downwards. That is again also due to pumping. There is lots of fine materials are being already pumped to the surface, and once there is any windy condition, it just goes away. So you don't see it. Sometimes you get to see it on the shoulder, especially for when it comes to when it comes to Portland cement concrete. But sometimes with hot mix asphalt, if it happens on the driving lane itself, you're just gonna get to see the depression most of the time without seeing the fines, because they're just they're gone by the time they are observed. But how can you distinguish this problem from others is really by seeing that depression at the crack. And again, you get to know that this is a pumping issue. When things again go a little bit even worse, this is now what you see here. This is the stripping due to moisture damage. As I said before, again, there will if water continue to penetrate through the hot mix asphalt, we're going to start now to see separation of asphalt from aggregates. So this is here. This is an aggregate piece. Same here. This is aggregates, and the darker part here. This is asphalt. And you would hope that there is always a good interaction, like what you see between this aggregate piece and it's surrounded by asphalt, 100%. You would assume that the same for all of them, except now this big aggregate in the middle, now there is air here. And this air eventually will be filled with water. Once we start to see that, then again, the water is gonna make it through the rest of the surfaces of the aggregate, and now we're gonna see what we call again moisture damage or stripping. Sometimes you're driving on the road, and all of a sudden, a little piece of aggregate just fly to your dashboard glass. Why is that? Again, it's stripping. The aggregate on the surface now is not really sticking to the asphalt anymore because of the poor drainage condition. How can you confirm that? Going to the field, besides just looking at some depressions, the cracks, you can also distinguish this by taking a core. Very famous way of doing it, although again, sometimes we call this a destructive testing, because we have to take a core and eventually we need to fill that very nicely. Otherwise, we're creating another problem, which is a pothole. But for now, if we are assuming that you're going to take a core, and let's say I know from the plans that I do have a hot mix asphalt layer with a 6-inch thickness, and then on top of a sub base or a base layer. So I'm gonna bring the coring drill, and I'm gonna try to take a core that is 6 inches. the length of it is 6 inches. What happens if there is moisture damage, like what you see here, you're gonna end up with, you're not gonna have a full core. Sometimes you're gonna end up with 2 or 3 inches intact inches at the top, and then the bottom of that core is gonna crumble by the time you're just gonna try to get it out of the hole. That is a big indication of having stripping due to moisture damage. So as you can see here again, the rest of the core is just bits and pieces already. If it's a good pavement and if there is no moisture there, you should be able easily to take that 6 inches as one big piece, and you can take it to the lab and you do further testing on it. But if it's just crumble by the time you get it out, that's a moisture damage stripping problem. Another indication is, even if you manage to get the whole 6 inches, whether it's one piece or multiple pieces, but at the bottom, like what you see in this picture here, there is water sitting at the bottom of that hot mix asphalt. At the bottom of that hole, you could see there is again lots of moisture. Or in some bad situation, even like this, again, it's just crumbly. You can hardly see asphalt. It's basically just crushed aggregates, although you're still coring within the top, let's say 6 inches or 4 inches of that hot mix asphalt. If you can't really distinguish aggregate pieces from asphalt, and it's just look crumbly, and it's sometimes we call it even like just a bird nest looking hollow, that's also another sign of having a stripping and moisture damage. Another problem that we see that's also related to pothole, related to drainage, is pothole, which is it's a mix between crack and moisture infiltration. Sometimes what happens is you're gonna end up with hair cracks. Sometimes we call them hair crack, or um, just random cracks on the surface. And if it's not treated at the very beginning, and that's why I mentioned briefly last week, in this class we're going to concentrate on the idea that fix the good roads first. If you start to see very small cracks, seal them. If you start to see the surface is not is getting a little rough, put a Fox seal or a seal coat on it right away. Otherwise, this is what happens. It's the mix between cracks and now moisture infiltration through the surface. You're gonna end up now with that pothole, and sometimes it actually it collects water, like what you see on this picture right here. Bad situation. Sometimes also we end up making those without realizing by taking a core. If you're going to the field trying to observe what's the problem, you take a core, and if that core is not filled very well, that is a weak point already that you're already creating in the structure. And if it's not filled well, if it's not compacted very well, again, it's a weak point because it's just a fill material that's not homogeneous 100% with what the rest of the structure is, and therefore that also can create, again, if it has higher air void, the water will get into there. One of the issues also, or one of the reasons of having potholes during compaction, if it's a poor compaction job, mainly on the edges of the right lane. Let me try draw for you this condition here. So if I have two lane roadway, one lane per direction, and we're doing a paving job, sometimes during paving, if it's just one lane per direction, we try to pave first. Again, we get the paver and we try to pave it all at once, especially if the length of each lane is somewhere between 10 and 12. What happens during this condition? We get the paver, the major part of the paver, the weight of the paver, the machine itself that pave and compact, is in the middle, and then it has almost like wings that also supposedly it has some weight, And sometimes you see the operators, some of the operators, they would sit here just to make sure that there is enough asphalt being spread all the way to the edges, but the amount of weight being applied on the edges is not even close to the amount of weight that's being applied in the middle part of these lanes. And what end up happens, so this is just paving, let alone now we come to compaction. We have the roller compactors or the pneumatic compactors or the rubber compactors. And also sometimes drivers, again, they get scared and they don't want to get closer and closer to the edge. So they try again to apply the roller compactor. Again, let's say if it's 2 rollers per machine. And again, they try not to be exactly on the edges. If the driver is not, again, if not experienced that much, again, things can happen. So what I'm trying to say is if this area, the edges are not getting enough compaction, they're going to end up with higher air voids compared to the middle part of the structure. And again, having lots of air voids, typically for any pavement structure, we try to design hot mix asphalt with 7% air voids. Those locations, they may end up with 9 or 10%, which means there's lots of air voids inside the structure, which is a very welcoming environment for water to get in and infiltrate. And if there is any point here or any batch that it's just not compacted as much as it's supposed to be, that's going to end up being a future pothole. Yep, that's a real sign that you can see. All right. Here, this is now thermal cracking. Thermal cracking is another one of the major problems that we face in flexible pavement. Thermal cracking, how can you distinguish it in the field? It's basically it's 90 degrees to the travel direction. That's what we call transverse crack. Sometimes we call transverse crack, and sometimes we call it thermal cracking. And they typically are very repetitive in nature. If you are just driving and you hear that effect of boom, 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 boom every 10 or 15 feet, very repetitive, exactly the same style, this is what we call thermal cracking. So distinguish it in the field, it actually, again, it keep repeating very regularly. Why does it happen? It happens mainly due to difference in temperature. So many of us think, and this picture definitely indicate or is biased that, okay, there's lots of ice or lots of snow. We see thermal cracking because of two conditions. The first one, if we have very cold weather all the time. Cold weather is basically, these are big areas of asphalt, and in nighttime or even during daytime, if it's just cold all the time, asphalt, as any other material in nature, is going to contract. You're going to try to contract. And that will actually generate lots of internal tension, internal tensile stresses inside the pavement structure. And since asphalt, which is different than pavement, the Portland cement concrete, we don't have the concept of a joint. It's a continuous structure. We tend to see that once the pavement reach its maximum tensile stresses, it's just gonna crack. Like this. And again, it's just some sort of stress relief that happens because of tension buildup inside the structure. That's the main cause of it, which is just continuously cold weather. Or it can even happen in the middle of the desert. It happens in Arizona, for example, because there is a huge difference between daytime temperature and nighttime. I lived there for 4.5 years. I know how it feels. In the morning, it's about 120. Sometimes we get these days 120 degrees. This is air temperature, let alone the pavement surface temperature, which is it reaches somewhere between 135 to 150. And at night of that same day, it can reach out, it can go down to 60 Celsius, 60 Fahrenheit. So that big of a difference, what we call this is the high temperature gradient. Within one day, I could see the asphalt is going from very viscous, very ductile in the morning at 135 degrees, all the way down to 60, where now asphalt start to be more brittle. And that also will cause the asphalt to contract at night time, and lots of internal stress is gonna build up, and eventually we're gonna have to exceed the tensile stresses and those structures, and then we see the crack. I'm showing you here some pictures because how severe it can be versus how low severity. We're going to talk about this in next chapters, but for example, this one right here, this lane, it's low severity compared to this lane right here. Now you could see that there is a distance here. This is what happens sometimes. The thermal crack will be just on the surface, or it can be, you can see the whole depth of the hot mix asphalt. This one is not, it's just maybe like the first half an inch or so, but the width of the crack here is significantly more than this part right here. And we're going to talk about this more, where every single crack that we see in the field, you need to classify it based on two things: severity and extent. Severity and extent. How severe it is, which is again how wide is the crack, versus extent. How again how what's the extent of that crack within certain segment, and these are two different things. Another problem that we see in the field is what we call reflective cracking. Reflective cracking is happens as follows. Again, I have a subgrade, I have a base layer, and then I have all pavement that is significantly cracked, and the crack is right here, let's say. And then one of the solutions, which is again, it's one of the easy solutions, but it's not that effective, is just to ignore the crack, or you say, you know what, I'm just gonna have an overlay. Let's have somewhere between 2 to 4 inches overlay, and cracks are going to be hidden, problems are going to be solved, and we're done. That is a big mistake, and it's just, again, it's just an illusion that's going to last maybe for 6 months or a year at the most. And sure enough, that crack, and that's why where the name come from, is going to reflect, is going to be reflected on that, in that overlay, due to tension and due to shear effect. To the shear effect. So basically, if you are driving any wheel, this is just a wheel load. You're gonna drive on that street, and once you reach the original crack location, that amount of load is gonna create two things. First, it's gonna bend the whole structure, and I'm just being exaggerating here, but basically, I'm gonna create a tension. Well, at the surface, there's compression. You're just compressing the surface, but at the bottom of the overlay, there is tension. And as we got to know, and we're gonna get to hear me a lot saying about hot mix asphalt, it's not good in tension. So I'm creating tension at the bottom of the overlay, and at the same time, that crack, we're gonna start to initiate and eventually reflect. I'm gonna also have a shear effect. The loaded part, which is if the tire is right here just before the crack, the loaded part is gonna be putting lots of pressure on this direction, while the unloaded part is gonna go up. So I'm gonna have that coupling effect, or the shear effect at the location. So if the crack was not fixed, or it was not sealed before we put the overlay, sure enough, that crack will reflect in the overlay in a very short period of time. Again, sometime just a matter of 3 months or 6 months, and then goes back up to the overlay again. So how can we fix the problem? is first is to fix the cracks first. You seal them, or you try even to, if the crack is not severe, which means if it's not so wide, you can seal it. Or sometimes what we need to do, if it's really a bad crack, you need to cut this piece, the whole piece, cut that, then patch it, and then put an overlay. But if you could see the crack, and if you can distinguish the crack, and you're just ignoring it, and you're putting an overlay on top of it, you're gonna end up with reflective crack. Other problem that we also see on the surface of the pavement is raveling. Raveling, again, it's another sort of progression, progressive disintegration of hot mix layer from the surface downward as a result of dislodgement of aggregate particles. It happens mainly due to low density. If the pavement is not well compacted, and that's why sometimes you have the best design, but if you're having a poor um, construction practices, you're gonna end up with problems. If this structure, for example, here is not compacted very well, and therefore you're gonna end up with high air voids, which means low density hot mix asphalt. Once the water penetrates through the surface again, you're gonna start to see again the aggregates now are gonna start to ravel, and you're gonna disintegrate from the hot mix asphalt surface. How can you distinguish it in the field? Again, the picture here will give you an idea, but also you're gonna start to see the surface starting to go to be as gray, very light gray, as you could see in these areas. And those light grays are gonna eventually turn into cracks or missing pieces. Aggregates are gonna be missing along along the way. That's what you how you're gonna distinguish raveling. How can you fix raveling? Again, fixing raveling probably is gonna be a mill and fill job. Mill and fill, which means if I have, let's say, this is again hot mix asphalt again. If it's a 4-inch raveling, as you see, as I read here from the definition, it's a problem from top. It's a top-down problem. So if you catch it, depending on how severe it is, if it's somewhere between low to medium severity, you need to do a mill and fill job, meaning that you're gonna mill or remove the top 2 inches and repave it again. If it's high severity and it's just again you're taking a core from here, for example, and the whole core is cracked across the board, then you have to remove the whole hot mix asphalt. If it's low severity, if it's very low severity, sometimes you can seal it. It's not a fog seal. We're gonna get to learn some of these techniques later, but fog seal or crack seal, but it's just across the board because it's not, you're not trying to fix a certain location. As you can see, the whole segment, you just need to be fixed up. So it depends again on the severity of the structure. It can go again as low as seal coat or as bad as just removing the whole thing. But typically, the more frequent solution that I've seen over the years is a mill and fill job where just again remove the top couple inches where the problem is and prevent the problem from extending to the rest of the structure, and then pave and repave that top 2 inches. This is here a high severity raveling. You could really see the aggregate pieces. Once you go to the field and you see aggregates and they are not covered with a very thin film of asphalt, this is raveling. It's high severity. You could see now the aggregates faces. They are not supposed to be this way. And with you, some engineers have seen, especially the experienced ones, they try actually to push the aggregate the surface with their shoe, and if the aggregate starts to move under their shoes, this is raveling. Again, now aggregate is not sticking with the asphalt anymore, and it needs to be fixed. All right, another problem here is block block cracking. Block cracking, the reason why we call them block crackings, because again, they look as if now the asphalt is being as little blocks. They can, if the blocks are big blocks, that's a low severity. That means it's not a bad, again, it's just starting. But as long as you keep it without fixing, those blocks are gonna get smaller and smaller, which means now again it's becoming again worse with time. Those are again block cracking. Block cracking, it can be actually is an extended problem from other types of cracking. It can be a thermal cracking as well as reflective cracking, and then if you really leave it for some time, they're gonna start to connect, and then they're gonna make those blocks. So it's a mixed problem with other types of cracks. How can you fix it again? Depending on the extent and the severity. What's the difference again? So severity is it's all about the 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 width of each crack. And I will share with you on Canvas um, the um, the manual. It's in a Federal Highway Administration manual. It's free. I highly recommend you look it up. It should be, you know what? This is again, you don't have homeworks, but this is your little homework here. Just type on Google LTPP manual or manual for distress manual, distress identification manual. Okay. LTPP identification manual. It's a PDF file, and you'll be able to see that there is there is for every crack there is a picture how to distinguish it and what's the severity level and what's the extent level of each one of the cracks. I may go ahead and show it to you also by the time we finish this lecture. All right, moving on to one of my favorite types of cracks. I spent 4.5 years of my academic career working on this for my doctorate degree back in Arizona State. Fatigue cracking. Fatigue cracking is a very big problem for hot mix asphalt. It had and basically it happens, and if it happens because of loading, and it happens because of just progression of time. But what is fatigue in general? Fatigue is basically again you thing a failure that can happen not because the stress is too much, it's because it's repetitive. If you go to the gym and you try to again you start warming up and now you're just gonna do dumbbells, it's 10 pounds. You're trying now to heat up the muscle, and then you've been it's just maybe 10 pounds, and you start now 10 times, 10 reps and 20 and 30 times, and then you start to get tired, and at a certain point you can't even hold you can't even hold that you can't hold that dumbbell anymore. That's 10 pounds. Although again, 15 minutes ago you were doing it very easily. Why? What happened? Your muscles got fatigued. It's not because the 10 pounds is too much.
I can hear you very well.
Yeah.
Uh,
Voice is going down.
can you hear me, guys?
It's
Still,
really low.
Say that again.
it's still very quiet.
Is it? How about now? Is it still the same? You can't hear me?
A little better, but not much.
Let's see here. Start to share. Mm, So again, so fatigue cracking. So basically, it's again back to that example. You can't handle the 10 pounds that you used to handle 15 minutes ago in the gym, not because 10 pounds is too much. It's because your muscle now is being fatigued due to the repetitive nature of the movement that you've been doing. Same thing, if you really want to have a piece of paper and you want to cut this paper into two halves, you can do it by simply having a scissor and you can cut it easily, or you can just keep bending it backward and forward and backward, maybe for a couple hours, and it's gonna get cut. Same thing happens for hot mix asphalt. Back to the structure that I drew it to you. So hot mix asphalt, and then I have a base layer, and then I have, let's say, a sub base, and then I have a subgrade. With the repetitive loading, once I have a wheel applied at any point on the structure, at the point of interaction between the tire and the surface of the road, I'm going to experience lots of compression. And the hot mix asphalt actually will bend this way. There will be compression on the top, but there will be tension at the bottom. So if you really draw now the bottom of the hot mix asphalt, you're going to start to see tension, while the surface there is compression. And we got to know again that tension is not is asphalt pavement cannot handle that much tension. So with the repetitive nature of traffic loading, small or big, what we're gonna see is the asphalt pavement now is gonna reach a certain tensile limit. We call it the endurance limit, beyond which the start of a crack will begin. What we call this is a fatigue cracking, crack initiation, and then with time it's gonna start to propagate from the top, from the bottom of the surface, from the bottom of the hot mix asphalt, all the way to the surface. So by the time you see this picture here, which happens most of the time in the wheel path, what does that mean? If you draw, if this is here at 12 feet, typically, this is a typical width of a lane. Most of the time, the major loading happens in the area of the wheel path of the vehicles. So the fatigue crack, this picture right here, you're gonna see this crack. These cracks happens mainly, or at least start, and in the wheel path, because again, this is just a plan view versus a cross section. This is here a plan view. And then once if it's left, then it's gonna continue to grow across the whole structure. In other places of the world, sometimes they call it alligator cracking because it looks like an alligator back. But the issue with fatigue cracking is once you see it on the surface, this is actually the end of the structure, because it's actually initiated at the bottom and it goes all the way up to the surface. So it's one of the most costly distresses that we see for hot mix asphalt is fatigue cracking, because by the time you see it, and if it's not well taken care of, you have to do a major reconstruction. So one of the solutions for fatigue cracking is actually to prevent it. One of the ways to prevent it, which we can talk about it later on, is how to make a thick of a section. If you make a thick section, you're going to improve the tensile stiffness or strength of the hot mix asphalt, because now increasing the thickness or doing other things like such as reducing the air void, making the section is a little bit stronger, you are gonna improve the endurance limit. The endurance limit, which is the strain value, the tensile strain. You're gonna improve the tensile strain or tensile strength of the hot mix asphalt, so that the crack will not even initiate at the bottom of the hot mix asphalt layer. So that's basically what is fatigue or alligator crack. This is here an advanced stage where again it starts, as you could see here, this is the end line, this is the edge of the of the lane. And again, this is mainly the wheel path, but it now is expanding all the way to the edge of that lane. So it's again, it's one of the worst case scenarios. Other problems actually that we're gonna see in the future, and there is lots of research going on, which is I thought it's fascinating to share with you. Autonomous vehicles. You've heard that before, which is again, we're not gonna be driving our own vehicles in the future. What does that mean? All these cars will be computerized, which means they are going to be almost, if not 100%, driving exactly at the same location in every single lane. What does that mean? It means actually we're going to have accelerated damage. Think about it. A human factor, for the ones who took classes with me before, I always say this is one of the curses of being a transportation engineer. You're going to deal with lots of human factors. You can design the best thing ever, but if you're having a bad driver, you're having a bad driver. A bad thing will happen. But the a positive side of having humans to drive rather than computers, we tend to have the blessing of traffic wandering effect. What does that mean? If I have a 12 feet lane, and Zabi is driving, and his driving is around here, and Jason is driving a little bit different, maybe 2 inches different, and Jade is maybe to the right by 1 inch. This is what we call the wonder effect. Every one of us is are not perfect, but it's in a good way, because now we're actually, as us as human beings, we're distributing more or less the damage across a wider area. Imagine now Jason, Zabi, me, and Jade are not on the road, and now computers almost the same, they think the same, and now instead of having this wide range of loaded area, which is gonna make fatigue cracking not to happen that quickly, now I'm gonna have the same four cars, but now all of them are gonna be exactly at that location. What do you expect? I'm gonna expect now an accelerated damage. So there is lots of research now. Yes, it's a good thing to have autonomous vehicles, but also we need to work on how can now we program the computers as part of being, of course, safe and efficient. How can we introduce that human wonder effect? So again, every vehicle is yes, it's programmed to drive safely, but also to have some sort of wonder distribution, and it's more or less like a statistical distribution if you think about it. Again, yeah, I mentioned four of us here that they can drive a little bit different, but eventually we have an average and we have a standard deviation. So that's what we're trying to do nowadays to introduce to introduce a man-made variance in driving unmanned vehicles, just to have less amount of cracks compared to if we just have all the vehicles driving exactly at the same location at the same length. Make sense? All right. Another problem that we see is aggregates. Polished aggregates. Sometimes, or most of the time, we tend to hear from the public that this road is too rough. The surface is just too rough, and therefore you're uncomfortable with driving. The vehicles driving on rough surfaces tend to go bad faster. You're gonna end up spending too much on fuel because now it's not really efficient. But the other side of that coin is to have a very slick surface, very polished surface. Once we start to have rain, like again today we're handling some rain, you will be driving in a very thin film of water. There will not be much interaction between the tire and the roadway itself, and that's a big problem. And that's what we see here, polished aggregates. If you go to the field and you start to see that again, you see shiny aggregates on the surface, that is a bad issue. The good thing it's a surface issue, so fixation is minimal, but you can't let that happen. Sometimes it's because of lots of traffic, it's because of poor mix design, you're selecting a bad aggregates, or you maybe the asphalt binder content is wrong. Basically, it's less than what it's supposed to be. So how can you fix that? Uh, Typically, an overlay would do the job if you have the fund to do it, or you can do a chip seal. Basically, chip seal is you're gonna have um, a thin emulsified asphalt, liquid asphalt, and then you're gonna drop one sized aggregates on the surface, and then you're gonna compact it very well. Once you compact it, so really this is it's a polished surface. You're gonna add emulsified asphalt, and then you're gonna drop one certain size of aggregates. So once you have those, they are the exact same size, and then you're gonna compress it, so they're gonna stick to the surface. So this is what's gonna restore the friction of the surface again. We're gonna have now a better friction one more time. Or again, this is one of the lower or less costly option. But of course, again, if you have more money, it's always the concept of having a 2-inch overlay on a structure like this would do the job as well. Other problem that's also very famous, and I think all of you have seen it, is high severity bleeding. Bleeding is basically again on the it happens if you're driving and on the wheel path, which is again 2 spots on every single lane. You see it's much more darker compared to the middle of the lane. This happens again, especially in hot weather. If the pavement now, it's a problem with mixed design. There is not much air inside, or there's too much asphalt binder. And there's too much asphalt binder, and it doesn't have a space to go, especially in hot weather. It's just gonna go to the surface. Why it happens in the driving lane or in the wheel path? Because this is where we're having lots of stresses. So if you look at the cross section, I have a wheel path here and I have another wheel path. There's lots of compression on the surface, and that compression again will generate that the binder is gonna try to expand, especially in hot weather, underneath that compression. And if it doesn't have a space to go, it's gonna end up going to the surface. So it's either high binder content and or low air void issues. How to fix it? A low cost fixation versus a high cost fixation. A low cost fixation, which is sometimes it seems ridiculous, is we just they bring it's like shaving blades on the surface. They just try to shave off that excess asphalt, liquid asphalt on top of at the surface of the pavement. So not much. All what they're doing again, they're trying to remove that extra pavement, extra asphalt that's appearing on the surface. Or better than this, again, is to have also a chip seal, the one that I just mentioned to you before, which is again emulsified asphalt. Or in this case, you're not going to put that much emulsified asphalt because asphalt is already there. You just need to add the chips, the aggregate chips, which is one single size, to improve the friction, because this problem is a big issue. Yeah, of course it does look ugly, but besides that, in rainy condition again or icy condition, this area is going to become very slick and it's going to become hazardous to drive on. So the best way again is to get rid of it by pretty much hiding it or removing it, all the way to an overlay. I've seen some DOTs, they just have some strict rules and they just add a couple inches of hot mix asphalt on top of it to fix the problem. bleeding slash again. So this is how bad it can get. If the asphalt now is too much on the surface and it's in hot weather, you're gonna even get to see that the tire is leaving some marks on the asphalt surface, as you see here. That's high severity bleeding. Rutting, another problem, very famous, one of the most famous problems as well. Basically rutting, let me draw you again. That's a 12-inch lane, 12 feet lane. And rutting happens on the wheel paths, as you may expect. It's basically a depression or permanent deformation on the wheel path. You get to see it much more when it's raining, where the water now is gonna start to be collected on those locations. And if you are driving, and again, let's say I'm drawing, oops. If I am drawing here a wheel path, and this is the wheel path again, there will not be much interaction between the tire, the rubber tire, as well as the roadway itself. You'll be driving again on a very thin film of water, and you're going to end up with a major problem we call hydroplaning. You're really now almost again flying on the road, not really driving anymore. And that is a very dangerous situation. What's the reason of it? Again, it's mixture design problems as well. If you have the bad binder content, again, whether again lower or higher, most of the time it's high binder content. If you have lots of binder, you're going to end up again with weaker spots. That doesn't mean the binder content is just low here at the wheel path, but it just happened to be signified there because of the loading. So rutting happens not just because of bad mix design, it's also it has to have repetitive traffic loading as well for the problem to show up. How to fix that, depending again on the extent of it. If it's just up to maybe 0.1 inch worth of rutting, sometimes we don't do nothing about it, or we start now to think of having other techniques such as a thin overlay. If it's a high severity rutting, you need to know what's the reason of the rutting. Is it a problem of the hot mix asphalt, or do we have problem now from the layers underneath the structure? And the only way to do that, or to get to know, is to do what we call a trench study, like this picture right here. This here shows you that you have to go to the field and cut through the pavement structure and see whether this rutting is across the board, across the whole layers, or just the hot mix asphalt. So rutting can happen. Let me show you now the two scenarios that you can see in the field. You can see something like this. So that means in this picture here, this means that the rutting is reflected across the board, from not just the hot mix asphalt, is the base and the sub base. You see the depression across the board. And this problem means that there's a problem with the subgrade. The subgrade is too weak, or there is drainage problems that's gonna lead, of course, with the effect of rutting, with the effect of traffic loading, it's gonna lead us to that the subgrade is the problematic part, because the whole structure is rutted. Or I can see this. Which means if I cut through, like actually in this picture right here, I see that the top layer is the rutted layer, but the base and the sub base, they are fine. Nothing is happening to them. You can measure the thickness here versus there, and it's the same. The problem is only happening at the hot mix asphalt layer. that's actually a better case scenario, because what happens in for case B, we just go to the field and we do a mill and fill job. We remove the rutted layer, whether it's 2 inches or 4 inches, and then we have a brand new layer. If for the case for A scenario, it's a bigger problem because now it's a subgrade. You need to remove the whole section. Whether again, I don't know how, depending on the extent of it, but again, if it's a 500, 600 feet long problem, you just need to remove the whole thing. Make sure that the water is not getting into the subgrade. Otherwise, you can see the same problem again once you rebuild the structure. So how to do this? If I ask you in an exam or an interview, you need to do what we call a trench study, like what you see in the picture here, in order to distinguish whether it's an A or a B scenario. Rutting also can happen at a utility cut, like what you see here. Again, it's basically, it's a weak point, and once it's loaded, asphalt is gonna show again that depression. That's rutting and at a utility cut. Another problem that we see, very interesting, it's linked to a problem that we've talked about in previous class. Not all of the ones here took 3351 with me before, but for the ones who did, we talked about what we call the dilemma zone. Dilemma zone, and when I'm getting closer to an intersection, we've all gone through this before. You're getting closer to the intersection, there is a signal, and it's about to get to be red. And you're thinking whether I just should speed up and clear the intersection, or hit on the brake and stop and wait for my turn next cycle. Most of the time, you're gonna decide either one of these two cases. But in some cases, you just get too confused, and that's why when you're so close, and so if you're far away, it's easy. You're gonna say, you know what, I'm gonna stop. If you're too close and you're just turning, you're gonna, again, it's easy also. But sometimes at certain distance, what we call the dilemma zone, it's very hard. And sometimes, and here, if you decide to stop very suddenly, you are going to end up applying a lot of braking forces on the surface of the pavement, and that's what's going to cause shoving. Basically, you're really applying lots of shear forces. Now let me draw this. So you're stopping, so lots of shear forces on the surface, and the bottom of the surface of the pavement is not feeling that much, but the surface does feel that. So you're gonna end up with what we call shoving. Again, the surface is almost like you ran through again a carpet that's really, again, it's just shoved and it's not exactly straight, and you're going to create that problem right there on the surface. One of the solutions for this is to use a stiffer binder closer to the intersection, this area right here. Or I've seen it in Nevada where the entire intersection, plus or minus, plus certain length away from the intersection, they pave it with Portland cement concrete. It looks interesting, but it works. So it's hot mix asphalt. Until you approach the intersection, and now it starts to be Portland cement concrete, because Portland cement concrete is not gonna shove. Shoving, again, it's a problem with lots of with viscoelastic materials such as asphalt. It doesn't happen to Portland cement concrete. But if you do have shoving already existing, and how can you fix it? Typically, again, it's a surface problem. So really what you need to do, again, it's a mill and fill job. You're gonna need to mill the top couple inches, and you're gonna have to fill it again. Another solution away from pavement engineering, going now to traffic engineering, is actually to improve the condition of the traffic signal timing. If you have enough yellow time, or you're having, if there's problems with sight distance close to the location, then again, if we improve that, we're gonna make sure that the drivers are not gonna deal with last minute or last second braking, and therefore we're not gonna see the problem again. So that's part of maybe preventing traffic rather than just fixing it, because once it happens, it happens. It needs to be fixed. Any questions about problems or distresses that we see for Portland cement concrete? I mean for hot mix asphalt.
I'm good.
Go ahead. Any questions? All right. So let's move on now to the Portland cement concrete distresses. How do they fail? Some of these failures for with pavement with concrete, they are similar to hot mix asphalt, and some other cracks that they are distinct to the Portland cement concrete. So the first one is transverse crack. Transverse crack is the same as hot mix asphalt. It's 90 degrees. The direction of it's 90 degrees perpendicular to the travel direction. It happens because the same reasons, and it happens because again, concrete as well as asphalt, they are not good in handling tension. So once tension is being built up because of temperature gradient, we start to see transverse crack. How can we fix that? If it's low severity, you can seal the crack. But if it's a high severity, you're just gonna cut this piece here. The whole piece is gonna be cut, and you're just gonna reconstruct it again. This whole piece is gonna be removed again. If you are not having a question, please mute yourself so it doesn't create noise to the others. Thank you. Longitudinal cracking. This is a problem that we see with Portland cement concrete. Basically, what happens with longitudinal crack is we uh, we pour concrete. The contractor will pour concrete, and then within somewhere between 24 hours to 48 hours, he or she has to come back and do the cuts. The those cuts here, those are the joint cuts. Joint cuts are really what I like to call them man-made cracks. Concrete as well as asphalt, but concrete is actually sometimes more dramatical. They will expand and contract by changing temperature, mainly. So what happens is if you pour in concrete and the contractor missed that period, sure enough, the concrete by itself, it doesn't need help from us human beings. It's gonna release that tensile stress that's built up, but of course in a non-uniform way, like what you see here. This is longitudinal crack. You typically are gonna see it along the structure. It can be miles and miles. And you're gonna ask me, so why we have here those joints? Sometimes again, the contractor he just wanted to come anyways. There is a crack. They just want to do whatever they're supposed to do, although it's late. But they just did it just to satisfy the job. But really, it's a late saw cut job, and that's why the crack will initiate. If it's a low severity longitudinal crack, typically we seal it. If it's high severity, we're going to end up with removing again the whole piece and reconstructing it again. Pumping, similar to what I mentioned earlier today, but for PCC, sometimes we see it more prevalent on the edge of the lanes or on the shoulders. You see here again, they are being repetitive in a transverse way, where the fine materials is being pumped to the surface by the water. And with time, again, we're going to see more of that. And then we're going to see again, the whole structure will sink. So that's how you can classify pumping. How can you fix that? Really, you need to fix drainage. It's a drainage problem that need to be fixed, and you need to improve the drainage. You need to get the water away from the structure as soon as it rains. Joint faulting. This is also another problem that's related to drainage problem, and it's related to pumping as well. Uh, Pumping happens sometimes or on the edges or on the shoulder. Joint faulting happens later on once we start to see more and more fine materials are being lost from one slab rather than the other. You're gonna start to see now that the slab that lost a lot of fines underneath it is gonna sink, while the adjacent slab it's at its original location, and therefore you're going to start now to see a difference in elevation. And that's why we, to identify this in the field, we just put a pin, and that pin, half of it will be touching or standing on the good slab, and the other half of the pin is just going to be on air, standing on air, meaning that there is now difference in elevation between these two slabs. That can be a hazardous situation, depending on the severity of it, especially again depending on the speed limit. Um, it's again it can be a big issue. So how to fix that? If it's low severity, sometimes we try to um, introduce lots of grouting, so we can mix a couple holes in that failed beam or failed slab, and we introduce cement paste. Basically, we're just trying really now to pump um, that much of cement paste to replace the amount of fine materials that was lost, hoping that this is now gonna introduce lots of pressure at the bottom of the slab to raise the beam. I mean, to raise the slab to the original location, or at least improve or reduce the faulting. But if the problem is really bad, we're gonna end up with replacing the bad slab, regardless of its length. Yeah, this whole slab is gonna be removed. We need to fix the problem drainage underneath it, and then construct a new one. But for the original one, you just can keep it as is. Corner breaks are again similar in a way to faulting. Sometimes again these locations, you're gonna end up with, if they are not really, when we pour concrete, if we may end up with some segregation on the corners or on the edges of the structure. If it's not really well distributed, and we didn't make sure that we don't have that much air voids in that location, and of course with repetitive traffic loading, you're gonna end up with that problem. Um, a famous way to fix it, as you can see on the picture on the left, is to seal the crack if it's low severity. If it's higher severity, again, we're going to end up with removing a big chunk of that slab, and you need to reconstruct it again. Joint spalling, another problem, where if we do not have a good joint, or there is drainage problems, and instead of having faulting, which is a difference in the altitude or elevation between two adjacent slabs, we can now have too much pressure, too much compression from each side of the slab. So once we start having that much pressure, again, bits and pieces from the surface will just come out from the joint, and again, this piece here is just gonna disintegrate from the surface because of too much compression, and not much here of stress relieving techniques are being introduced. How can you improve it? You can improve it again by, you're gonna cut through the joint here, improve the joint condition. Again, have some materials such as rubber or some synthetic materials to improve the compression situation here. Or if it's very severe, you're gonna end up with replacing the slab that's highly affected with spalling. And again, if the joint is really now is not a joint anymore, and it's just the two slabs are just hitting each other literally, we're gonna end up with spalling again due to what we call joint lockup. Lockup now again, it's just the two slabs are locked up, and um, any movements from trucks is gonna just generate spalling because there is nothing that can um, take that much compression anymore. And if things are really left without any fixation whatsoever, I hope you don't see this in any project, but it does happen every once in a while. Is what we call blowups. This is now it's just a high severity spalling slash flushing slash all the problems before. You're gonna again spalling as well as joint spalling and corner breaks and faulting. If all of these are left for a long time, you're gonna end up with what we call again blowups. It's just the whole most sometimes we call it buckling, but buckling we like to use that word more for columns and structures, but actually this is buckling in a horizontal direction, where again the two slabs are just they can't live with each other anymore. So that's what happened in this picture. It can be upward like in the picture in the bottom, or it can be downward like what we see here at the picture at the top. And I think the fixation for this problem. Really, the whole structure here has to be rebuilt. You need to compact the subgrade really well. You need to make sure that the drainage problem is being fixed. You need to have a strong base and sub base, and then you're gonna pave it whether with hot mix asphalt or with Portland cement concrete. Alkali silica reactivity, sometimes if you pick the wrong aggregates, it's gonna react badly with cement. So that's why we call it alkali silica reactivity. Again, this is a chemical side effect of dealing with again certain aggregates that you have to avoid if it has lots of alkali, because silica is what's in cement. Cement has lots of silica, and if I have aggregates that's rich in alkali, that's a big problem. You're gonna end up with lots of hair cracks. That's what we call them at the beginning, but eventually they're gonna expand, and you just need to be again. You need to replace the whole structure here because you're just using the wrong aggregate type. Sometimes we call what we see, and again, don't mix these two up. Alkali silica activity, it just hair cracks across the board. But the durability crack, or what we call now decracking, this is now due to moisture damage and freeze thaw or susceptible aggregates. So basically, if we have drainage, water gets into the joint, so now moisture problem, and then with that we also have if we're in a location that's now it get lots of snow, or we reach freezing temperature, freeze and thaw cycles, as well as bad aggregate sources, that aggregates are susceptible to be broken, or they are not really strong enough. We're going to end up with those durability or decracking. We call it decracking or durability. Again, the way you distinguish them in the field, they're actually forming the letter D from both directions. That's what we call the decracking. How can we fix such cracking? Really, the way to fix them is you're gonna dig deep and remove the whole piece, and then you want to make sure that you are not using that susceptible aggregates again. Big problem here also punch outs. It's again you need to replace the whole structure here. It's the same thing. It's not designed well. The joints are not there to take in that much compression, and that's what you end up with again punch outs. So I think again with that we finished the second part, of this chapter, and next time again we will go on chapter 2.